Okay, so today what we're going to do is we're going to talk about reaction rates and what determines it and how are they impacted by the thing. So, first of all, you need to be aware of, and take a look in video 2 notes, turn to them now please, is that we define the reaction rate as the change in concentration of a reactant or product per time. So, if you take a look at this graph right here, do you see how we have NO2 over here? And it is a reactant, and it is going to NO and O2. I think this needs to be balanced by putting a 2 here maybe and a 2 here, but I think that's how it would look. So if you can see here, if we start off here with our reactants, wouldn't it make sense that at the very beginning we have the highest rate of disappearance of NO2, and then over time as we have less and less, our reaction rate goes down. Then if you take a look at our products, and there are 2 different products here, we have one for NO and we have one for O2. Now if you take a look at this here, doesn't NO require 2 NOs for every 1 O2? And this is kind of cool because if you take a look at this, this should disappear twice as quickly as this should, right? Because it takes 2 of these for every 1 of these. If you take a look at the graph, it does show, and this is kind of a weird curvy graph, so it's not a straight line graph, but over time, do you see how this is, I said disappeared, but what I really meant was formed, sorry. So NO is being formed here at a faster rate than O2 is. Yeah? So this is interesting because whenever we start talking about reaction rate, the instant that this reaction starts going like this, we start getting products, and a lot of products, aren't they reversible? Right? And so as soon as you start getting products over here on this side, right, all over here, I don't know why I'm drawing like this, but let's say you start having products over here, then these guys right here, they're going to want to react and reform over here. Now, if you're trying to figure out the rate of reactants forming, I don't know what that, reactants forming products, right? Let's say you want to have a rate for the reaction occurring. You want to know how long it's going to take before NO2 gets to NO and O2. You have a problem because at the very beginning of the reaction, all you have is NO2 forming products, but then the reverse reaction starts coming back and it starts hurting your overall progress. So this is a problem for us, and it's certainly going to affect your rate when you have products reforming your reactants going back in this direction. So the chemistry gurus, they came up with an idea, and this is actually really, really clever. They decided that they would do all of the reaction math always at the instant that the reaction started. So there'd be no products to worry about. So it kind of makes sense, and what's really interesting is that in every single kinetics problem you're going to see, you're never going to see concentrations of products in any of your rate reaction problems. Why? Simply because we are not going to worry about them because we know that it would impact our overall equation. So what I do need you to understand is this, and this is incredibly important. I decided not to have you do a lot of fill in the blanks so you can kind of highlight things that are going along here, but you know how we did in equilibrium, we used coefficients a lot to help us write our equilibrium expressions or law of mass action or whatever else. But in kinetics problems, we do not use the coefficients except in one case when we're dealing with multi-step problems. But as far as we're concerned, right now, we are not going to use the coefficients as part of our equations. Now, before I get to how we work with that, let me just point out a couple of things that impact the rate of a reaction. This is kind of a big deal for us. I kept them in here, but some of the stuff makes pretty good sense, right? So if we have the concentration of something increases, the more concentrated our reactants are, the faster reaction goes. That makes sense. If we increase our concentration, our reaction is going to go far faster. If we increase our temperature, don't the individual reactants speed up, and then they have more collisions, so they move faster, and therefore they'd react more. The physical state, powders react faster than blocks, and if you think about it, if I have powder right like this, all these individual particles are going to react better than if you have a box, because if you think of box, all these particles here in the middle, they're not going to be able to react at all. And we're going to talk about this a little bit later on, if you have a catalyst or an inhibitor. So reactions often have catalysts, and you probably learned this way back when. A catalyst is something that makes a reaction go, but itself is not included in the reaction. We'll get to what that actually looks like in the couple videos from now. There's also inhibitors. So you may be like, yeah, I don't want this reaction to go as quickly, and so you can slow the reaction down. I would say of the two of these, the catalyst is by far what we use way, way, way more. And finally, light. It's kind of weird, but if you have particular wavelengths of light, which don't we know that light is energy right now, that can also speed up a reaction as well. So we could have just said if you add energy to a reaction, you can cause it to go more quickly. So let's move on to the next slide here. And I want to take a look at the example they give you in the textbook. And I want to say that it is, I think it's 12.2. And look, I have written there. So if I were to look at this right here, I want to point out to you how we write a rate law. And this is really a big deal. So all of our rate laws are going to have this function. It's going to be written like this. It's going to be written rate is equal to some constant, and every rate law has a particular constant, and it's going to be multiplied by the concentration of the reactant only raised to some power, some order. Now I want to point out something here to you. See how the number right here is 2, and I did not put that number in there at the top? That's because, again, we do not use coefficients in our equation, which begs the question, what the heck do we do with this m? How do we figure it out? So unfortunately, the way we're going to figure out the data in this is we have to actually get it from tables and information they give us. What you should know, though, is if you're ever asked to write a rate law expression, it's always going to take this form. What they will expect you to do, though, is they'll expect you to have this m right here, which we call the order. Will expect you to have that. They'll expect you to have that filled in. Now, there are two types of rate laws that we're going to talk about. One are differential rate laws, and they are, I'm right, differential, it's hard to write and speak at the same time. Differential rate laws, I'm not going to write the whole word out, and they show how rate is dependent on concentration. In fact, we actually, whenever we talk about a rate law in general, we're talking about differential rate laws. So differential rate laws and rate laws, they go hand in hand. That is kind of how we, in the future, that's all we say, that's all we talk about. Integrated rate laws, they show how concentration depends on time. And these are much, much more tricky. And they are, if you're good with calculus, then you're going to love this stuff because you have done integration before, and this will be wonderful for you. But for right now, I'm going to leave both of these types of reactions alone. And we're going to talk, we'll talk in the next video on how do we figure out the rate law from data. Just like I said before, again, hopefully this has been helpful. I'll see you in the next video. Thanks. Bye.